Okay, good morning, everyone. First, thank you for the introduction and thanks for the organizing committee for giving me the opportunity to present part of my PhD research that I'm conducting under the supervision of Dr. Jordi Juarez and Dr. Javier Baril. Today, my talk is entitled Multiple Copies Association Studies, a computational approach for binding mode elucidation. I'm actually quite happy that my talk is coming after the previous talk because I was gonna say that for me, binding mode elucidation is one of the key steps and very important factors in every structure-based drug discovery campaign. So for instance, I will give you some examples. Imagine you have an attractive protein target and you have identified some hits for the target. You got yourself some binding affinity data and you're very happy and you want to continue from hit to lead optimization. So in this case, if you aim for a structure-guided approach, you would want to experimentally find where your hits bind to your target. And this is all very good, but as we heard from the last talk, sometimes experiments don't go as planned, and you might find yourself in a situation where you cannot definitively know where your hits bind to your protein. So this is one scenario. Imagine another one. You have a protein target and you have your pocket, and you want to design ligands for this specific pocket. You might start from virtual screening or go for some already known ligands that you want to optimize. And then you have some experimental validation, and you find out that your ligands that you designed do not bind to this pocket, but actually bind to another part of your protein. And again, experimentally, it's hard for you to know where. Actually, in both of these cases, you might be dealing with allostery. And actually, in allostery, it's much more important to elucidate the binding modes of your protein ligand systems. So these are only two scenarios. There are many others in which binding mode elucidation experimentally is challenging. So to address these challenges, we envisioned a computational workflow that combines classical molecular dynamic simulations and high ligand concentration. The idea behind this idea is that you can simulate your protein of interest with multiple copies of your ligand that you want to identify the binding mode for. And by doing this, you enhance the sampling of ligand binding events, and you can get your hypothesis of the most probable binding mode much faster and with much better convergence. So having this idea in mind, we designed our workflow, which starts with system preparation, of course, where we place our protein of interest, solvating it in the ligand that we want to identify the binding mode for. And here we have a step of adjusting the parameterizations of our copies, of our ligand copies, to limit the aggregation of the molecules during the simulation, and to keep the effective concentration in order to sample the protein surface. Then we perform multiple replicas of unrestrained all atoms classical molecular dynamic simulations. And as a step after that is to cluster the ligand positions along the simulation, which we do by using density-based clustering. And as a last step, very important, we perform a lifetime analysis of these clusters, our probable binding modes actually, to identify the most populated ones and the most stable ones, which will then give us an idea of the most probable binding mode of this ligand. Having our designed workflow for this multiple copies association studies approach, we wanted to validate it. And to do so, we used actually 5 different protein targets with in total 23 protein ligand systems. So different proteins with different ligands that have reported to be positive in NMR. And also they had experimental crystal structures so we could compare with our simulations. I want to show you just a couple of examples. For instance, in HSP90, we had 6 binders, and we identified the binding modes for 5 of them. And for instance, for one of them, we could only identify the binding site. We also had 2 kinase cases we chose, and we also got some very positive results with the workflow. Just to let you know, the green structure is the crystallographic one, and the colorful one is the one from the simulations. And here in the DIRC1A kinase, we also had a fragment with a carboxylic acid moiety that actually, when it was deprotonated, we could not identify the binding mode, but when we neutralized the ligand copies, we got the exact binding mode. Then we thought, oh, this is a limitation of the method maybe. But then in our P1 case study, we had 4 binders all with carboxylic acids, and without neutralizing them, we actually managed to recover the crystallographic binding mode. And then as a 5th protein case, we chose a WD repeat domain, which is a bit more flexible, and we got also some very positive results. So in total, in our validation, in 22 out of the 23 cases, we identified the binding site, the true binding site from the crystal. But in one case, we couldn't identify the binding site. And then in 18 out of the 23 cases, we recovered the crystallographic binding mode that was reported using our mass workflow. So having this validation, we are still developing the method, of course, and looking for its limitations. But we are now using, and actually you were all the time with this. Yes. We are using the mass workflow for some of our in-house projects and collaborations. For instance, we are using mass to identify the binding modes of some novel FBW7A3 ligase fragment hits that were very challenging to identify the binding modes experimentally. So we are doing that. As well, in our lab, a colleague is designing novel binders for VHL, and she's also validating the binding modes using the mass workflow. And as a 3rd project, we are collaborating with the group of Professor Rademacher, where they are trying to design ligands for a C-type lectin protein, and they wanted our help to identify the binding modes of their ligands because their NMR data was not concrete. So this is about my method and the projects that we do. I would like to thank all my group from Barcelona and my 2 supervisors for all the support, and of course the ALLODD consortium, amazing team, and thank you all for listening as well. Thank you.
What I'm interested in, I think it was super nice that you can get use remote binding modes. But of course, you also get a lot of other, let's say, solutions. So do you see trends to differentiate 2 binders or have the more possible?
So what you are asking is if our other legal positions, our other possible binding laws, if we can clearly identify the true one from the other ones that are being sampled. In some cases, it's actually very clear based on the lifetimes, the population of the binding mode and the stability. It's very clear. In some cases, not so much. And it depends on the protein ligand system, on many things.
Now, curious, so is there a difference in the frequency and lifetime? Is that target dependent, or is it relative for one target, or will you see similar trends of different targets you have thrown out?
So, from my experience with all the systems, it depends on the protein target, of the pocket, of the flexibility of the ligand and the protein as well, conformational change. Also, it is, by my experience, also dependent on the affinity of the ligand, because there are some trends where very, very weak binders are like the populations and the stability is much lower than in very, very strong binders, because we have differences in all of these cases. But it depends on many things. Yeah.
Thanks for a very clear talk. So you have the first series of tests where I think the reference compounds were mostly in the allosteric side, like for kinases and HSP90, which implies that this does not require reorganization of the protein. But for some allosteric binders, you typically need protein reorganization, which implies a much longer time space for your MPs. So have you tried to do some tests which would be more difficult with two allosteric binders?
You mean to add two different molecules, or to have that you have two different binding sites?
Yeah, we're trying to reproduce binding to sites which typically require protein reorganization.
Mm-hmm. Yes, for sure. If a conformational change is needed, it might be much harder to get the binding. So in the HSP90 case, for instance, we also have a conformational change that is happening very close to the binding site. Well, not like a, no, like in the pin1, it's an allosteric site. It's not the orthosteric site, but it's very shallow. So, and it's very exposed. So it doesn't. You mean like cryptic pockets, maybe, or
yeah.
Yes, no, we haven't tried with like very, very challenging like cryptic pockets. The case of the ALLODD repeat domain is also a secondary binding pocket, but it's also on the surface of the protein. So no, I guess we haven't tried that.